Today we'll look at how planes can intersect each other, and there's 5 different ways that that can happen, and these are all shown here. With one of these, there is a unique point where there's one solution to the system of 3 planes, and that's when they intersect as such. They don't necessarily have to intersect at right angles, but it's possible that all 3 share one point. It's also possible to have infinitely many solutions when the planes come together to form a line. So they all share a line in common. That would be infinitely many solutions, and we can express that line in a vector form. The rest of these have no solution. There is no point that is shared by all 3 planes at the same time. And one thing to note is this case up here, the 3 planes are parallel to each other. This one, there are 2 parallel planes. This one, there are no parallel planes. So how do we tell if planes are going to be parallel to each other? Well, their normals need to be parallel. If the plane's normals are parallel, we know that there aren't going to be any solutions. If at least 2 planes have parallel normals, we know there can't be a solution to the system. So, enough talk. Let's look at some examples. You've done this before, I hope. We're solving a system of equations. So here are 3 planes given by 3 equations in x, y, and z. The solution to this, if we solve this using elimination, is 1, 1, 1. So going back to our diagram that we just saw, visually that's happening right here with this one. I'm not going to go through how to do that. I'm going to hope that you can. We are going to go through the solving process with the next 2 examples though. So here's a new one. I want you to pause the video and see if you can't solve the system and come to a conclusion about what kind of solutions it has. Alright, so here's what I'm going to do. I'm going to eliminate y. So I'm going to take equation 1 and equation 2, and I'm going to eliminate y in them. So multiply the top equation by -2, we get -6x minus 4y minus 2z equals -2. We add these together, we get x plus 3z equals 1. And I'm going to take equation 1 and 3, and I'm going to eliminate the same variable. And this should be nothing new. So I'm taking the top equation, multiplying it by 3, bottom equation by -2. The y's go away. I have -x minus 3z equals -1. So now I have the equation, the system, x plus 3z equals 1, -x minus 3z equals -1. And when we add these together, we get 0 equals 0, which tells us infinite solutions. And up until, I don't know, maybe you did this, maybe you haven't, but we just said infinite solutions and we're done. Well, if there's infinite solutions, that means that these planes intersect to form a line. Let's find the line. So here's what I'm going to do. I'm going to say, let z equal lambda. If z is lambda, that means that x is equal to 1 minus 3 lambda. And I can go back up my equations here, and going back to the very first equation, I can get that y is equal to, if I substitute these two parametric equations into the first one, we get y equals negative 1 plus 4 lambda. All right, now we have parametric equations for a line. I can write a vector equation. We'll call it r equals 1, negative 1, 0 as the emanating point, plus lambda times the direction vector, negative 3, that's the coefficient of lambda, for x, 4, and 1. So infinite solutions that all lie on this line right here. Next example. We're going to solve this one. So again, pause this video and see if you get the same thing that I do. So I chose to get rid of my z first, and I ended up with the two-variable system, 4x plus 3y equals 4, and 8x plus 6y equals 1. If you chose to eliminate another variable or use different pairs of equations, that's fine. We should still end up at the same spot. So I'm going to multiply the top one by negative 2. We get negative 8x minus 6y equals negative 8. We add together and we end up with 0 equals negative 7. What? 0 doesn't equal negative 7. I know, right? So there's no solution. Now the question becomes, which of those three no solution cases is this? Do we have any parallel planes? And the way we tell that is we look at the normals of these planes. The first plane has a normal of 3, 2, 1. So if any other vector is a scalar multiple of that, if any other normal is a scalar of that, they're going to be parallel. And 2 is 1, 1, negative 1. Those two are not scalar multiples. Those two are not parallel planes. And the last one, and 3, the third normal, 5, 3, 3, and that isn't a scalar of either of the other two. So none of these planes are parallel. The situation that we're looking at is that one right there. Now, it is possible to use a graphing calculator to solve these systems, and I want to look at that very quickly here with this last example. So in my calculator, I'm going to go into Menu, Algebra, Solve System of Linear Equations. Number of equations, we're going to have 3. We're going to have x, y, and z. Okay. And I'm going to type in my equations. So there we are. We have them typed in. I push Enter. No solution. Look at that. Wow. If we're allowed a graphing calculator, you'd be a fool not to do this with your calculator. With the infinite solutions, it becomes a little bit more involved because it doesn't tell you what the equation of the line is. That's something that you will have to do yourself. But it will tell you if there's a unique solution or no solutions or infinitely many solutions. And there we go. It's where I'm stopping. You got to be careful with all of this algebra. That's where you're going to make mistakes. Have a wonderful day.